All right, let's dive right in. We're about to pull back the curtain on a massive, hidden crisis that's been slowing down scientific progress for decades. But more importantly, we're going to look at the revolutionary AI that's finally starting to fix it. You've probably wondered this yourself, right? With all our incredible technology, why does it feel like finding a new cure or making a big biological breakthrough still takes forever and costs a fortune? Well, the answer isn't a lack of data. Turns out, it's a problem of pure, unadulterated chaos.
I mean, look at this. On one hand, the goal seems so simple. You just want a single, clear answer from all the biological data out there. But then, wham, the reality hits. Researchers are trying to get that one answer while juggling more than 11 completely different, totally incompatible data sources that just don't want to play nice with each other.
And this mess has a name: the biological data fragmentation crisis. See, the problem isn't that we don't have enough information. Oh no, we're practically drowning in it. The real issue is that none of the data can talk to each other. It's like having all the pieces to the most important puzzle in the world, but they're all cut differently and you can't make any of them fit.
Think about it this way. Imagine you have to write a critical report, but all your source books are in 11 different languages, and you don't have a single dictionary. That is the daily nightmare for scientists. Every major database speaks its own language, has its own rules, its own format. It's a digital Tower of Babel, and it's brought progress to a crawl.
Now, this digital chaos isn't just some minor inconvenience. It is a massive, billion-dollar bottleneck. So let's actually put some numbers on this and see just how staggering the cost is every single year.
Okay, first up, just the cost of inefficient data access. We're talking $30 to $90 billion. But here's the real kicker. That's not the cost for the entire industry. That's the annual price tag for a single large pharmaceutical company. Just one.
And it doesn't stop there. All the time scientists waste just trying to fight with the data, that adds up to another $25 to $75 billion in lost productivity. And again, that's per organization, per year. It's insane.
And finally, before any real science can even begin, these companies are spending another $18 to $55 billion a year simply cleaning up and fixing the data they already have. You add it all up, and the financial drain isn't just holding us back, it's actively preventing breakthroughs.
So all these crazy costs really boil down to these core issues. You've got siloed access, you've got inconsistent formats, performance bottlenecks. But the most shocking one, the one that's a real tragedy, it's knowledge fragmentation. Get this, somewhere between 80 and 95% of all biological knowledge is just trapped, useless, locked away inside these digital silos.
Okay, but what if you could change all that? What if you could build a universal translator for every last piece of that data? Well, that's exactly what we're looking at now. A system designed from the ground up to make every single database speak one unified language.
So how does this thing actually work? Well, the idea is beautifully simple. Step 1, you unify access to all those different databases. Step 2, you standardize everything using APIs. Think of them as digital handshakes to create that common language. Step 3, you unleash a powerful AI to read, understand, and connect all of it. And finally, step 4, you deliver it to scientists as a single, clean source of knowledge. Now, the AI doing the heavy lifting here is called an LLM RAG system. And that RAG part, Retrieval Augmented Generation, is the game changer. It means the AI isn't just making stuff up. It's actively pulling real-time, verified facts from all those databases. So the best way to think about it is like this. Imagine a super librarian, one who's read all 2.3 million biological research papers ever published, has perfect memory, and instantly sees how every single discovery connects to every other one. That's the kind of power we're talking about.
And this system is designed to do one thing: to finally crack open that vault and unlock that vast ocean of knowledge. That 80 to 95% of information that's been trapped for decades, it's finally being set free.
So what happens when you finally tear down that digital Tower of Babel? When you completely remove the single biggest bottleneck in all of modern science? Well, the result is a leap in productivity that's, well, it's almost hard to believe.
Yeah, you're seeing that correctly. The potential jump in research productivity is estimated to be between 2,000 and 5,000%. Let that sink in. No, that's not a typo. It means a research task that used to take years could now take days. This changes the very speed of science itself.
Just look at this direct comparison. It's absolutely stunning.
research productivity goes through the roof. The cost of just integrating data, it plummets by up to 99%. And the overall speed of discovery can accelerate by up to 95%. This isn't just an improvement, you guys. It's a complete reinvention of how research gets done. And let's be really clear here. This is about so much more than just being faster or cheaper. We are witnessing a genuine research revolution. This kind of technology fundamentally changes what's possible, the kinds of questions scientists can even dare to ask, and the answers they can actually find.
And in the process, it's not just shaking up an old market, it's creating an entirely new one. This is the birth of a whole new economic sector that's being built around this idea of biological intelligence.
And the scale of this new market? It's enormous. Just look at the projections for 2028. The top 3 markets this tech creates, infrastructure, processing, and platforms, are expected to be worth a combined $700 billion. This is the engine that's going to fuel the next generation of scientific discovery. So we end on this thought. For decades, we've been trying to piece together the language of biology from millions of scattered, disconnected fragments. Now, for the very first time, we have a universal translator. The only real question left is, what do we want to ask it first?